Hi everyone, welcome back to another video. Today we'll be looking at the grade 12 physical science paper 1. We'll be focusing yet again to the electric circuits. Okay, so this is going to be the 2023 May-June question paper. Let's look at the statement. The statement reads as follows. A battery with an unknown EMF and an unknown internal resistance is connected to 3 resistors. Okay, let's have a look at the diagram. They are saying there is a battery with an unknown EMF. There is the battery, and then this battery has an internal resistance. Okay, so we're looking at this section of the circuit. All right, so in this diagram, there are 3 resistors which are connected. There are resistors 1, 2, 3, and also there's a high resistance voltmeter. Like we all know, or as I've explained in the previous videos, of which I'm going to attach the link in the description below. Please refer there to what we mean by a high resistance voltmeter. Okay, there's also 2 switches here and 2 ammeters. Okay, let's have a look at the switches. There's switch S1 and then the switch S2, and then there's ammeter A1 and there's ammeter A2. All right, before we go deep into this question, just a minor explanation on what we mean by a switch. Okay, in this moment, if we look at switch S1, we are seeing it drawn like this. There's 2 modes of a switch. If we mainly focusing on this kind of a switch, can it either be like this or be like this. So this we call open, and this one we call closed. All right, so it tells you that in this circuit the switches are closed, and when the switch is closed, or you can see continuity within this path, it means current is flowing. Okay, I just wanted to explain that when you look at switches. And then they are saying ammeters. Ammeters measure current, so the current that passes through that specific part of the circuit is going to be measured by the ammeter that is connected along that path. So if we look at ammeter A1, it means that ammeter A1 measures literally current that passes through it, which means we're looking at this part of the circuit. Ammeter A2 measures current that passes through it, which means we're looking at this segment of the circuit. All right, let's move on to the first question. First question is question 8.1, which is asking us to state Ohm's law. By now you should be very much comfortable with our previous sort of theory around Ohm's law. I said to you, for you to understand Ohm's law, you need to think of a conductor, a resistor, and then a voltage source. So that can be your battery, a conductor, and then a resistor. Ohm's law says that if you have a resistor that is connected this way, and on that resistor there is current that is moving this direction, and as you know, the current will pass through that resistor there and go back to wherever it is coming from. Let's indicate it as I, and then let's indicate this as R. When we talk of resistance, and this is purely for English, if we say that this person is resisting the law, it means that that person is making it hard for the law to be applied onto them. If we say a resistor is resisting, in the case of Ohm's law, in case of circuit theory, we're saying it is resisting the flow of current. It means that it doesn't want the current to flow. All right. So when we talk of Ohm's law, we need a law that is going to relate these two. Now, Ohm's law tells you that when there is more resistance, it becomes hard for the current to flow, and that is simple. So in laws of, or in just normal physics terms, we say that current is inversely proportional to the resistor, meaning when there's too much resistance, the current will be small. Okay, so Ohm's law is saying that a current carrying conductor, the current through that conductor is inversely proportional to the resistance and direct proportional to the amount of voltage that is being passed through that circuit. So if you look at where this current is coming from, if you connect a V there, we're now saying that in a current carrying conductor, the current is inversely proportional to the resistance and directly proportional to the voltage. So if you look at this, we're saying I is inversely proportional to 1 over R, and I is directly proportional to V. Meaning that if we're saying there's too much resistance there, then you say, you know what, I'm going to increase the force at which I'm pushing you through that, call it a gate. It means that now we'll have much more current that is going to flow in there. Meaning, if I'm saying it is hard to go through that path, and mainly because it is too small, what I'm going to do is that I'm going to push you through that path. So if we relate voltage to resistance, voltage is the force that pushes the current to flow, or call it electrons to flow, or charges to flow. If the resistance is resisting the flow of those charges, it will mean that I need to push more to get past that. So current is directly proportional to voltage and inversely proportional to resistance. So we can state that Ohms law states that in a current carrying conductor, the current is inversely proportional to the resistance. It can be resistance of that conductor or resistance of whatever resistance is connected to that circuit. Okay, to the resistance and directly proportional to the voltage. Okay, one thing I haven't mentioned in here is that we are assuming that this is all, what is this, honey and juice. But we don't live in a world like that. It can be raining, it can be very hot, it can be windy, and you ask yourself, then what do those conditions, how do they impact Ohm's law? So Ohm's law is mostly true, or is only true when we are saying that the temperature, or provided that the temperature remains the same. Because when you increase the temperature here, funny things or interesting things start to happen in a circuit. So you need to state that, provided that the temperature remains the same. There are other quantities that might affect this, but let's stick to temperature for the scope of what we're looking into. So you have to include there, provided that the temperature remains the same. All right, now we're going to move on to question 8.2.1. Okay, the statement of this question reads as follows. They are saying that both switch S1 and S2 are closed, and the reading on ammeter A1 is 1.5 amps. Okay, so we can label it here now that we're looking at, okay, through this ammeter, we're looking at 1.5 amps flowing there. All right, and I told you for current to be able to flow, this circuit needs to be closed, or this switch needs to be closed. Okay, they're saying we'll close this, we also close that one. Okay, so they're saying, tell us about the reading on voltmeter, on the voltmeter. Okay, where is the voltmeter? Let's go to the circuit. This is a voltmeter. Where are its legs connected across? The first leg is here. It goes on this part of the resistor, and it goes to this part of the resistor. Okay, if I ask you, is this point different from this point? These points are just connected by a mere wire. This is the same as this. So if you look at the current here, it's just the same. Which means I might as well just remove this voltmeter and connect it like this. Because this point and this point, they're just connected here. They are the same point. I can also remove this leg of this and connect it here. Do you agree with me that this point here is the same as this point, same with this, and same with this point? But it's not definitely not the same as, let's say, this point of the circuit. Why am I doing this? Now you start looking at the voltmeter in a different way. This voltmeter is measuring the voltage across here and across this part of the circuit. And we said that a voltage in a parallel circuit. So the voltage on one leg of the parallel circuit is equal to the voltage on the other. And this is the reason. It means you can just connect the voltmeter across this side and this side, you'll read the same voltage because these are connected on the same point in the circuit. This is not the same as saying I'm connecting a voltmeter here. Now you're talking of another thing, which is what I'm not mentioning. Okay. Now, why am I saying this? We're supposed to look at the reading on this voltmeter, which means if there is current flowing here, we can measure the voltage or potential difference across this guy, but we don't have any current flowing here. All right. If we don't have any current flowing here, we can look at this part of the circuit because it's also included by whatever is being read by that voltmeter. Okay. So we can say this current that flows through A1, the potential difference V, the reading on the voltmeter is equal to current, the current passing through A1, this current passes through this resistor, and comes back to this point. So this is the same current. Doesn't go to the voltmeter. Well, if you want more information about why current doesn't go through the voltmeter, just check the links that I will attach in the description. Okay. Now we're looking at the current, specific current that is passing through ammeter A1. This current multiplied by resistance will give us the voltage that is being read. Let's note this. Let's say this is 8.2.1. Okay. The current through those resistors need to give us the reading on the voltmeter. Okay. But what is the resistance I'm looking at here? R is equal to the summation. These are series resistors. So it means I need to sum these guys to find the total resistance that this current will have to face. And remember, I told you from first that current has to pass through a path of certain resistance. If you plug in lots of resistors, it means I need to count the effect of all those resistors to prevent that current flow, or to make it hard for that current to flow. So if I look here and I just say this is the R that I'm looking at, I'm not being fair because the current goes through this resistor and goes through this one. So I need to sum those two. Okay, so to sum those is 2 ohm plus 5, which is 7 ohms. All right, so I can substitute this back here. We know the current through the ammeter, we're told, is 1.5. This multiplied by 7, then we can have a look at how much that is. Okay. 1.5. Okay, that is V is equal to 10.5 volts. Okay, that is the reading on this voltmeter here, 10.5 volts. All right, now let's have a look at question number 8.2.2, which is the reading on the ammeter A2. 8.2.2. What is the reading? What is IA2? Okay, so let's look at where is this ammeter they are referring to. We go to this circuit. There is A2. Where does A2 sit? Oh, A2 sits along this line. Now, if I ask you, is this line the same as this line? No, it is not, because it is separated by the battery. Okay, but if I ask you, the current that flows here, the current through ammeter A2, is this current here the same as this current there? Yes, it is, because these are connected in series. There's no branching here. When you talk of a parallel circuit, we say when a current gets to a certain point, it now starts deciding where must I go. In this case, it just continues to flow. All right. So if we were to follow the current, this A2 till this point, we can see that this current is still motivated to go here. Right. When it gets to this point, the interesting point, it asks itself, okay, I'm here now. I'm current. I know that a path of more resistance makes it hard for me to flow. Then it starts deciding, okay, do I go this direction or do I go this direction? Means some of it will have to, because it can't fit in here because there's still another path here to flow. Some of it goes here and we know how much that current is that goes to this side. It's 1.5 amps. But there's another current we don't know that is flowing through this side of the circuit. Let's say I of 3 ohms. There's I that flows through 3 ohms there. We don't know the value of that I. Okay, but all we know is that if we were to sum these two currents, because they move here, this one gets to this point, this one goes here and gets to this point, they have to meet again, they sum there. Which means that they go back to the current that we started with, which is A2. So it means IA2 is the summation of the current through the 3 ohm resistor, plus the current that goes through the circuit, of which we know it is 1.5 amps. All right. Now, question you're asking me, how do you calculate the current through the 3 ohms? What is the formula for current? Current is called voltage over resistance, or potential difference over resistance. So it means if we were to get the value of potential difference across a certain resistor and know the resistance, then we can find out the current that flows through that path. We get to this point. Do we know the potential difference across this resistor? We can look here. Do we know what is measuring the voltage there? Maybe you might say, we change the circuit, it gets hard. But if you look at this voltmeter is connected across this resistor. Remember from the first drawing, this voltmeter is just here. Meaning that we can say that I3 ohm is equal to V over R. We know V, which is the potential difference across that 3 ohm. It is the same as the potential difference across this side of the circuit. And how much is that? That's what we calculated here as 10.5 volts. 10.5 volts. Then the easier question. What is the resistance of that resistor? 3 ohm. Alright. So 3 ohm, which means we can calculate the current, and that is going to give us that is 3.5 amps. Therefore, we can come back to our equation here and say 3.5 amps plus 1.5 amps. This is going to be 5 amps. That's the current through, or that's the reading on ammeter A2. Ammeter reads current, so the current through that ammeter is 5 amps. All right. Let's move on to the next question, which is question 8.2.3. Okay, now in this question they're asking you what is the power dissipated in the 3 ohm resistor. Besides going deep into what power is and all of that, ask yourself what is the relationship between power and resistance? How can we find the amount of power dissipated on a resistor if we know the resistance? Okay, there's various equations. The first one is this: power is equal to I squared multiplied by R. Second one is that power is equal to V squared divided by R. Right. The last one is power is equal to V multiplied by R. But in this case, we're given a resistor, so we can focus on these first two. But even in those two, you need to choose which one would you like. And just to make my life simple, I'll just go for the second one. Why that? We just did a question now. That one does to calculate the reading through ammeter A2. But we had to speak about the 3 ohm path, this path. And here we knew the potential difference across that resistor, and also know the resistance of that resistor. So we can go for this equation. Another person would be like, but we calculated the current that flows through this path, and we know the resistance. So I might as well just choose this. And another person can say, you know what? I know the potential difference across here. I know the current that goes there, so I can just go through this. So you can choose any path that you like. I'm going for this one. power is equal to V squared. What is the V there? Is 10.5 volts. There, we calculated it. 10.5 volts squared divided by the resistance, which is 3 ohm. And this is going to give us all right. This is 36.75. We're calculating power. We're looking for watts. Okay. All right. Now we are moving to the next question. Okay. This question is saying, now switch S1 is opened. Switch S1 is opened while switch S2 remains closed. Let's go and open this switch. I showed you how to open a switch. This is an open switch. This is a closed switch. Open the switch. When you open a switch, there is no flow of current there because there is no wire connecting the two circuits. All right. We're keeping this one S2 closed. So we can already tell from here that current moves here and then ask yourself how much is going to go this side and how much is going to go this side. And then finds out that there's no path to flow here. Why would I go there why would I drive my car there when I know the bridge is collapsed? Okay, so it doesn't go there, all of it goes through this side. So we can already know that the current flows that side. Okay. Now they're asking us to calculate the EMF of the battery. They also mentioned that the reading on A2 now changed. The reading on A2 is now 3.64 amps. Okay. Now reading is 3.64 amps, and we're meant to calculate the EMF of the battery. Okay. So what is the formula for EMF? Or what is an EMF? I always mention, and if you get stuck, go back to the previous videos. An EMF is the voltage or the characteristic of the battery that you're buying. You go to the store and you look there, you know what, I want to buy a battery for my car. How much volts does the car need? Oh, 15 volts. I go to the store and ask the teller there, where can I get a 15 volts battery? They show me, they give me, they say this is 15 volts. That is the EMF. Okay. Now, over time, there will be things that develop on that battery. We have corrosion, we have a lot of things. Then it starts to have an internal resistance, which is what we're talking about here. So meaning that if you take this battery and connect it to some circuit, it won't give you that 15 volts you once were promised. But does it change the fact that from the factory it was designed to be 15 volts? When you look at the stamp, there is written 15 volts, and that's what we mean by EMF. Right? Meaning that for EMF, we need to always sum two things. EMF is equal to the voltage that is being read by the external circuit, which I'm using the battery for, which is the V external, plus whatever is being eaten by, I don't know what it is, maybe it goes inside the battery. Okay? But we call that the internal resistance. Internal resistance is a resistor. To make that to be voltage, you need current. All right. This is the formula for calculating an EMF. All right. So this guy will always be the same. Will this one be the same? No. Will this one be the same? This depends on time. Okay. Now, what do we have in this circuit? In this circuit, we have a new system here. We have current flowing through this path. Current flowing through this path. How much is that current? Is 3.64. Okay. So V external is equal to the current external, or let's call it current IA2. Right. Multiplied by the, for voltage, you say, to calculate voltage, you say current multiplied by resistor. And what is the resistor in that part? It's the 3 ohm resistor. So I times 3 ohms. Right? plus I times what? I external, because the reason why I'm saying is I external is the current that passes through this resistor comes, all of it goes through that internal resistance. So these currents are the same. We say this multiplied by R. Okay, we're looking for E. If we substitute here, we have 3.64 multiplied by 3 plus 3.64 multiplied by R. And this is going to give you 3.64 is going to be 10.92 plus 3.64 R. Now it seems like we have a problem there. We're solving for EMF, but there's still an unknown figure there, which is the internal resistance. Now we look there, did they tell us how much that internal resistance is? No, they didn't tell us. Okay. But the good thing about all of this circuit and why I had to take you through the theory of what an EMF is. The same battery that was connected here of a specific EMF E is the same battery that is connected on this new circuit now. You changing these switches doesn't change the fact that this battery was always off that specific EMF. Meaning that we can go back to this circuit where S1 was closed and S2 was closed. Because here we have two unknowns, and for one to solve two unknowns, we need two equations. So we need to find another equation that is going to represent the EMF of the battery and still have that internal resistance that we don't. Then we can start doing our simultaneous equation and solving for R. Okay. So if we can go back to this equation here, we needed same thing. So let's call this equation 1. We needed E equals to V external plus I external multiplied by internal resistance. This is still the same internal resistance, same EMF. What is the external voltage? External voltage, remember, we once asked to calculate the reading on this voltmeter. This voltmeter, I said to you, you can connect this voltmeter in this position, you can even connect it here. Because these lines, all of these lines here, all of these lines, if we look at this line, even on this one, the potential here is the same. These are just lines. Meaning that when we read the voltmeter here, when we read the voltage on this voltmeter, we were talking about the external voltage. Because it is, when you talk of external, you have to ask yourself, what are we external to and what are we internal to? We're talking about external to the battery. So the voltage external on the battery is the reading on that voltmeter. And we know that reading was 10.5 volts. 10.5 volts. Plus, what was the current flowing through that internal resistance? Remember, this circuit is in series, this part. Meaning that current we're calculating here for A2 is the current that flows through that battery or through that internal resistance. Okay, so what is that current? We found that current to be 5 amps. So we have 5 amps here multiplied by internal resistance. Then we have our equation 2. Now you can start solving for R and E. But the question is asking us to find the value of the EMF. So I'm going to try to make R to be the subject of the formula there, so I can just go straight to calculating the EMF. Alright. So if we take this equation, we can say, if you take this 10.5 this side, you'll have 5R equals to E minus 10.5. Solve for R. R is equal to E over 5 minus 10.5 over 5. And this is the same as just saying E over 5 minus, then you can work that out. So we divided by 5 on both sides. And that is E over 5 minus 2.1. And that is our equation 3. And to solve this, you substitute equation 3 on equation 1. Don't substitute equation 3 on the same equation that you use to calculate or to make the same quality equation. So we take this and substitute it to equation 1. So E there would be equal to 10.92 plus 3.64 multiplied by E over 5 minus 2.1. To solve this, let's go 10.92 plus so it's going to be 3.64 multiplied by this one, 3.64 multiplied by that one. And that is going to give you 0.728 E when you multiply this by this one. When you multiply this by 2.1, you're going to get minus 7.644. And remember that this was the minus sign. Don't forget that. Okay, so since we're solving for E, we need to take E to this side. We're gonna need another space here. Okay, let's take out this one. So continuing this to this part of the board. Okay. So for that, we can take everything that has E to the left. So it's going to be E minus 0.78728 E equals to 10.92 minus 7.64. 10.92 minus 6.74 minus 7.64 going to be 3.28. So this is 1 E or epsilon minus 0.72 epsilon E. So that's going to be 1 0.272 E equals to 3.28. And E there, you're going to find by dividing by this number on both sides. Alright, that is going to be 12.06 volts. Okay. Now that is the solution for question number 8.3. All right. Okay, so in the statement, they are saying that switch S2 is now opened. Where is switch S2? Switch S2 is opened. Okay. S2 open. S1 is closed. All right. Now, how does the voltmeter reading change? Choose from increases, decreases, or remains the same. So let's try and draw this circuit because it's a little bit tricky now. We come here, the voltmeter. Okay, so we look at this circuit here. So I told you, when we open this switch here, when we open that switch, we have cut off that whole circuit because no current is ever going to flow there, right? Which means this is the same as just going to the last circuit there and having your A1, have your resistor, first resistor, second resistor, and come back. So if you look at this circuit here, it is open. There's nothing that goes there. And then where is our voltmeter? Here's our voltmeter. All right, this is 2 ohm and 3 ohm. All right, so they're asking how does this affect the reading on this voltmeter? Okay, cool. Let's try and analyze this guy. First thing, when we cut off one part of a parallel circuit, we increase the resistance. Let me try and repeat that. A parallel circuit has a total resistance of R parallel. 1 over R parallel is equal to 1 over R1 plus 1 over R2 and so on. But internal series resistance is just R total, or R series is equal to R1 plus R2. There is no division or anything in here. And you'll know that a current that encounters a parallel circuit has two choices: go on the side of less resistance and go on the side of more resistance. That's why I'm saying to you that the current has more choices of being on the side of low resistance. But when the circuit is open like this, there's no choosing. You have to go through the path that you're provided. Right? If we cut off this side of the circuit, we're gonna face 3 ohms. If we cut off this side, we're facing 5 plus 2 ohms, meaning we're facing 7 ohms. Right? Okay. Now let's try and analyze how does that affect the external circuit. So remember, I told you that EMF is equal to V external multiplied by O minus plus I external multiplied by internal resistance. Right. Remember, I told you that the internal resistance here, or the EMF of the battery, doesn't change because the circuit is changing. It will remain that EMF that you bought the battery to be. Right? Meaning, if we were to look in this equation, this side must always be maintained to be the same. And this must be maintained to always be the same. So we're left with two things here. We're left with I external, which is I external multiplied by the R external. Remember, we're saying that this one must remain the same and this one must remain the same. So the guys that are changing here is this one. And if R external increases, remember these are inversely proportional. When external resistor increases to this resistance here, current will have to decrease. Alright, so if we take and make this to be the major, the main equation, we put I external here multiplied by R external. This is our V external. This is going to be E, which is the same, minus I external. As far as I R. Remember, these are remaining the same. And I ask you, when you increase resistance, what happens to the external current? When you increase resistance, current will decrease. Increase the resistance, current will decrease. Meaning, this portion decreases. When the external current increases, when the external resistance increases, the external current decreases. So if you look into this equation, if this is supposed to remain constant, and this is supposed to remain constant, and this part decreases, it means that this is growing bigger. So if you look at, say, 12 minus 1, that is going to be 11. But if you say something is taking out this side, is decreasing this, and now we have 12 minus 0.5. This will be 11.5, meaning this side has increased. So if we have this new circuit here, we are now effectively increasing the external resistance. And when you increase the external resistance, the I external decreases. And when it decreases this portion. And since the EMF will always remain the same, the V external will increase. Right. So that is the answer for our last question. This same question we have looked into, or same format of answering it on the previous videos, which I'm going to also attach the link on the question on the description below. So thank you once again, and please remember to like, subscribe, and please write up some questions that you might have on the comment section, and we can start addressing those. But we have a new format today. I'm going to ask the crowd if they understood anything or they have any questions, so we can directly address that. Okay, now let's address my crowd. Do you have any questions?
No.
The crowd is satisfied. Are you satisfied? All right, we'll see it on the comment sections below. Thank you.